Alright everyone, welcome back to Cody's Lab. So as you can see, we're using the vacuum chamber once again, and I actually have a little feather right there, as you can see, suspended in front of a 12-volt electric fan. See, I got the batteries, a pressure gauge, and everything in there. To turn it on, I have a little tilt switch that is magnetically controlled. You can see when I turn the fan on, it blows the feather all over the place. This is, of course, at atmospheric pressure right now. So, I want to take this down to Martian conditions. You might have noticed the Martian reference over there. The first thing I'm going to do is add a little bit of dry ice to the chamber, just so that the atmosphere gets replaced with CO2. Many of you guys were complaining about that last time. So now I should have a CO2 atmosphere, or at least it'll create one. And now we're going to suck out all of the air, or at least most of it, down to the point for about between 4 to 6 millimeters of mercury, which is, of course, the pressure on the surface of Mars. So let's plug in the vacuum pump. There we go. Give this a little while to suck down. These pieces of CO2 look really interesting in the vacuum. The gas produced causes them to levitate and float all over the place. But if you can see the gauge over there, you can see that the air pressure is just about to the point where it would be considered the surface of Mars. So since we're at Martian air pressure, let's unplug the vacuum pump and let's turn on this fan. Now place your bets as to what's going to happen to this feather. Now the fan's only going to produce maybe 10 miles per hour worth of wind. On the surface of Mars, the fastest recorded wind speed is about 70 miles an hour. But let's say the superstorm in the Martian had wind speeds of 200 miles an hour, 20 times what we have here. To compensate for that, I imagine the feather is about 20 times easier to push over than a spaceship. So let's see what happens. Okay, fan's on. And the feather's not moving. In fact, let's zoom in on that. Not even flinching. Let's turn the fan off. Okay, and let's turn it back on. So there you go. Now, extrapolating from that, you can imagine that even a 200 mile an hour wind on Mars isn't going to do much. Of course, Andy Weir had to figure some way to strand Watney on the surface of the planet, so I'll let him slide on that one. So to finish up this experiment, I'm going to turn this fan back on, just like this. And now I'm going to let the air back in, and let's see what happens as we come back to Earth. Yeah, almost immediately you can see the feather start shaking around more and more violently. Okay, so the air stopped coming into the chamber, so now everything's due to the fan. What I think is interesting is the fan actually sounds different. It doesn't vibrate quite as much. I guess it is designed to run in an atmosphere. So there you go. The air density has a big impact on what wind velocity actually does. Hope you all enjoyed. I'll see you next time. Such as gunpowder. See, this is a mixture of charcoal, sulfur, and potassium nitrate. When heated, the potassium nitrate gives off oxygen, which the sulfur and charcoal uses to burn. So I've got a little bit sitting in there. Let's apply the laser goggles, and let's light it off. First in the atmosphere, and then in the vacuum. Okay, as you can see, it produced lots of smoke and burned rather quickly. Most of the air is now gone. Let's see what happens. The gunpowder did not ignite. I saw some smoke coming off of it, so I know it burned a little. Let's try again more in the center of the pile. And that's it. The gunpowder does not burn. I mean, it burns when the laser's on it, but other than that, no. It doesn't change from one particle to the next. That's interesting. So Scott Manley actually messaged me and asked if I could try rocket fuel in this test, and so I'm going to be burning some rocket candy. This is a mixture of sugar, potassium nitrate, and iron oxide. This is used in amateur rockets because the ingredients are readily available and the amount of thrust it produces is quite high. So let's light this on fire and see how it does. So this is in Earth atmosphere. As you can see, it burns rather rapidly, producing a little bit of thrust even. As you can see towards the end, it moved it around. So now let's try it inside of a vacuum. No ignition. That's interesting. I did see some little poofs as it tried to burn, but it was unable to sustain itself. So even when it's in one solid piece, it can't chain and continue burning. Acetone peroxide in the atmosphere in 3, 2, 1. Yes, that's a little bit more volatile than gunpowder is. Acetone peroxide in vacuum in 3, 2, 1. It still didn't burn. I'm actually disappointed. You need something to confine it in order to get it to burn and then eventually explode. And at atmospheric pressure, the atmosphere does it, but in the vacuum, there's nothing there. So far, nothing I've tried has been successful, but I was thinking about it, and everything I've tried up to this point has produced gases as a product of its combustion. So I thought, what if I tried something that didn't produce gases? How about some thermite? This is a mixture of iron oxide and aluminum. Well, normally this is actually magnesium powder because I didn't have any aluminum on hand. But the idea here is that the reaction will not produce gases. It might make a little bit, but primarily the product of the reaction is going to be molten iron. And molten iron, of course, it's not a gas, so it's not going to leave as quickly, so maybe it can help chain the reaction along. So let's test this out. This is a thermite reaction in Earth's atmosphere. Here we go. That burned up. I can see that there's little bits of iron, some magnesium oxide floating around. A little bit of smoke, but again, that's probably just from contaminants that burned up. So there we go. Let's try it in the vacuum. I did not get an ignition. I see pieces flying all over the place, but none are actually igniting.